Next part is the hydrostatic equation, part 3. Hydrostatic equation. We consider a small fluid element. In this case, it's like the cube of the fluid, that the size of this cube fluid is del x times del y times del z. Okay? And if the pressure on the top is P top and the pressure on the bottom the P bottom, and the density of the fluid, we can find the low naught is the take the average between the density of the top and the bottom. Okay. For the vertical force is equal to F plus F from the pressure is the different pressure from bottom and top, and for the weight is equal to average of density times the volume. Okay, and we take equilibrium, the F pressure plus the F force, F weight equal to 0, and so we take we substitute the F pressure and F weight. You can see that F dy dx cancel, dy cancel, so we can prove that the dp over dz is equal to minus rho naught g. In case it depends on the direction. If we assume that the z vertical is positive and g is this direction, so we got the negative side. But if we assume that positive downward is positive and g is a downward, so we can say that it's a positive side. Okay, so that is normally we use this to use for the hydrostatic force. Okay, in this case is we assume that z is positive, is upward, is the still negative side, and we can substitute in this grid number P1 and P2 and Z1 and Z2, and we can say that this the difference Z1 and Z2 is equal to P2 gamma divided by B1 gamma is we call the pressure head. Okay, and this fluid diagram showed to derive the pressure at depth h. Okay, we apply this, use this equation, dp over dz equal to rho g. The integration between PA is P atmospheric pressure to P at the depth h, okay, from 0 to h. So we can write that P over PA is equal to rho GH. So in this case, P is the absolute pressure. And P subtract PA is the gate pressure. Okay, and this one we can write, so that is okay, there is a P subtract PA, just this part equal to, oh, it should be this length, sorry. Okay, P subtract PA equal to rho GH. So normally rho is a constant, density of fluid is constant, so we can say that the pressure increase linearly with the depth. Okay, and we can say that Pz equal to gamma h. Okay, and can we to understand this more clearly, we can look at this. This is what we call the hydrostatic pressure distribution, the different point. For example, at the point A, B, C, D, they have the same depth. Depth is H is a water, and the top of water is atmospheric pressure. We can say that the PA pressure at the point A is equal to pressure at point B equal to pressure at point C, and because it's the same depth, okay, equal to rho GH, okay, because of equal depth. Okay. And for point capital A, capital B, capital C, capital D, we say that the PA is equal to PB and equal to PC. But how about PD? Because of density, because of this part is filled with the mercury, so we have a different low density, so we expect that the density of the mercury is higher than water, so we expect that the pressure at point D is greater than point C. And sometimes we use the datum to different the depth of the set 1 and set 2 for comparison between the depth of water at different points. Okay. Summation pressure in continuously distributed uniform static fluid vary only with the vertical distance and independent of the shape of the container, as I show you in the above figure. Pressure is the same at all points on a given horizontal plane in the fluid. The pressure increases with the depth in the fluid. Okay. And this shows the coordinate system for air and water. Normally, for air, we say that P is upward, vertical is positive, so P is equal to P subtract at this point B, gamma of air. Okay, so it means the pressure decrease with the height of from the surface. But for water, we use the downward is positive, so pressure is equal to PA plus gamma water times H. Okay, that is difference between the pressure of air and pressure of water.